Let's look into NAND gate SR flip-flop. The SR flip-flop is considered as one of the most basic sequential logic circuits. The flip-flop is 1-bit memory bistable device. It has two inputs. One is called as set, which will be set the device, that is output will be 1, and it is labeled as yes. The other is known as reset, which will reset the device, that is output will be 0 and it is labeled as R. The RS stands for set or reset. The basic NAND gate RS flip-flop circuit is used to store the data and thus provides the feedback from both of its outputs again back to its input. The RS flip-flop actually has three inputs: set, reset and its current output Q, which is relating to its current state. A pair of two cross-coupled unit NAND gates is the simplest way to make any basic 1-bit set or reset RS flip-flop. It forms set or reset bistable or an active low RS NAND gate latch. The feedback is fed from each output to one of the other NAND gate input. The device consists of two inputs. One is known as the set, that is yes. The other is called as reset, which is R. The outputs are Q and Q bar. The state. If the input R is at logic 0 and input S it as logic 1, the NAND gate Y has at least one of its input at logic 0. Therefore, its output Q must be at logic level 1. So, this is the basic principle of a NAND gate. The output Q is fed back to the input A. Both the inputs of the NAND gates are X at logic 1 and therefore, its output Q must be at logic level 0. The reset input R changes its state and goes high to logic 1 with S constant at logic 1. The NAND gate Y inputs are now R equal to 1 and B equal to 0. The output at Q remains at high or logic level 1 as one of its input is still at logic level 0. As a result, there is no change in the state. Therefore, the flip-flop circuit is said to be latched or set with Q equal to 1 and Q bar equal to 0. Let's look at the reset state. In the second stable state, Q is at logic level 0 and its inverse output Q is at logic level 1 and is given by R equal to 1 and S equal to 0. As the gate X has one of its inputs at logic 0, its output Q must be equal to logic level 1. This is also according to your NAND gate principle. The output Q is fed back to the input, so both the inputs to the NAND gate Y are at logic 1, therefore Q is 0. If the set input S now changes the state to logic 1 and the input R remains at logic 1, the output Q still remains low at the logic level 0 and there is no change in the state. Therefore, the flip-flop circuits resets the state that has been latched. It can be seen that when both the inputs S equal to 1 and R equal to 1, the outputs Q and Q bar can be at either the logic level 1 or 0, which depends upon the state of the inputs S or R before this input condition existed. Therefore, the condition S equal to R, which is equal to 1, does not change the state of the outputs Q and Q bar. However, the output state of S equal to 0 and R equal to 0 is an undesirable or an invalid condition and it must be avoided. The condition wherein S and R both are equal to 0 causes both the outputs Q and Q bar to be at high together at logic level 1 when we would normally want Q to be at the inverse of Q bar. The result is that the flip-flop loses the control of the Q and Q bar, and if both the inputs are now switched high again after this condition to logic 1, the flip-flop becomes unstable and switches to an unknown data state based upon the imbalance. This imbalance can cause one of the outputs to switch faster than the other, resulting in the flip-flop switching to one state or the other, which may not be required state, and the data corruption will occur. This unstable condition is generally known as its metastable state. Then, a simple NAND gate SR flip-flop or NAND gate SR latch can be set by applying a logic 0, which is nothing but 0, the condition to its set input and reset again by then applying a logic 0 to its reset input. The SR flip-flop is said to be an invalid condition if both the set and reset inputs are activated simultaneously. SR flip-flop using NOR gate. So let's now discuss about it. SR flip-flop can also be designed by cross-coupling of two NOR gates if it is an active high input SR flip-flop. The operation is same as that of the NOR SR latch. So let's look at the first case. When both set and reset inputs are low, then the output remains in the previous state. That is, it holds the previous data. Next case, when the set input is low and the reset input is high, then the flip-flop will be in reset state, because the high input of NOR gate with R input drives the other NOR gate with 0, as its output is 0. So both the inputs of the NOR gate with S input are 0. This will cause the output of the flip-flop to settle in the reset state. The third case, when set input is high and reset input is low, then the flip-flop will be in the set state itself, because the low input of the NOR gate with S input drives the other NOR gate with 1, as its output is 1. So both the inputs of NOR gate with R inputs are 1. This will cause the output of the flip-flop to settle in a set state. The last case, when both the set inputs and the reset inputs are high, then the flip-flop will be in an undefined state, because the high inputs of S and R violates the rule of the flip-flop that the outputs should complement to each other. So the flip-flop is in an undefined state, which is also called as a forbidden state. Even though simple SR flip-flops and simple SR latches are same, both the terms are used in their respective context. The problem with simple SR flip-flop is that they are level sensitive to the control signal, which makes them a transparent device. In order to avoid this, gated, or you can go with a clocked SR flip-flops, which are introduced. Whenever the term SR flip-flop is used, it usually refers to the clock SR flip-flop itself. Clock signal makes the device edge sensitive and it has no transparency. Clocked SR flip-flop. The two types of clocked SR flip-flops are possible, based on the NAND and based on the NOR. The circuit of the clocked SR flip-flop using NAND gates will be considered. This circuit is formed by adding two NAND gates to the NAND based SR flip-flop. The inputs are active high as the extra NAND gate inverts the inputs. A clock pulse is given as input to both the extra NAND gates. Hence, the transition of a clock pulse is a key factor in functioning of this device. Let's assume a positive edge trigger device itself. From the truth table, we can see that when the clock is not provided, there is no change in the state of the flip-flops. When the clock is provided and S equal to 0 and R equal to 1, then the flip-flop is in the reset state. At the arrival of the clock, when the input S equal to 0, 1 and R equal to 1, then the flip-flop is in steady state. When S is 1 and R is 1, the state is forbidden for this set of inputs. The same can be achieved by using NOR gates too. The figure suggests a structure of the RS flip-flop. The functionality of the set and reset remains the same. When S is high, Q is set to 1 and R is high, Q is reset to 0. So let's look at the applications of an SR flip-flop. As a digital latching relay, it can be used. SR flip-flop is used in the digital logic circuits for the switching or the circuit breaker to hold the closed state even after the input controlling signal disappears. As a switching mechanism for alarm circuits, that is, when an alarm is pressed, it will not get reset until the reset button is being pressed. Let's look at D flip-flop. One of the main disadvantages of the basic SR NAND gate bistable circuit is that the indeterminate input condition of the set equal to 0 and reset equal to 0 is forbidden there. This state will force both the outputs to be at logic 1, overriding the feedback latching action, and whichever input goes to logic level 1 first will lose the control, while the other input still at logic 0 controls the resulting state of the latch. But in order to prevent this form from happening, an inverter can be connected between the set and the reset inputs to produce another type of flip-flop circuit, which is known as the data latch. Sometimes it is also known as the delay flip-flop, or simply a D flip-flop as it is more generally called. D flip-flop is by far the most important of the clock flip-flops as it ensures that inputs S and R are never at equal to one another at a particular time. The D-type flip-flops are constructed from a gated SR flip-flop with an inverter added between the S and R inputs to allow for a single D input. Then the single data input labeled as D and is used in the place of the set signal, and the inverter is used to generate the complementary reset input, thereby making a level sensitive D-type flip-flop from a level sensitive SR latch as now S equal to D and R equal to D bar. We remember that a simple SR flip-flop requires two inputs, one to set the output and one to reset the output. By connecting an inverter or a NOT gate, so the SR flip-flop we can set and reset the flip-flop using just one input, as now the two input signals are complements of each other. This complement avoids the ambiguity inherent in the SR latch when both inputs are low. Since that state is no longer possible, thus this single input is called the data input. If this data input is held high, the flip-flop would be set, and when it is low, the flip-flop would change and become reset. However, this would be rather pointless since the output of the flip-flop would always change on either of the pulses which is applied to this data input. To avoid this, an additional input called the clock or the enable input is used to isolate the data input from the flip-flop's latching circuitry after the desired data has been stored. The effect is that the DE input condition is only copied to the output Q when the clock input is in active.